In a paper that is just online in separation and purification technology, the development of a cadmium MOF that is ultramicroporous and contains accessible oxygen sites is described for the task of producing purified methane from a mixture containing methane, ethane, and propane. In this presentation, I discuss the procedure that is adopted for evaluating the performance of cadmium MOF for this separation task. I list here other video presentations that provide a background to the evaluation methodology that I am suggesting here. In the published literature, most papers that describe the synthesis of a MOF for a specified separation application follow more or less a standard template. This standard template consists of measurements of unitary isotherms of each of the guest molecules in the MOF at 2 or more temperatures. The most commonly used procedure for determining the heats of absorption involve the use of virial fits of the isotherms at various temperatures. The unitary isotherms at any specific temperature, usually 298 Kelvin, are fitted with dual-site Langmuir-Freundlich isotherms using commercial software. Based on these DSLF fits, the IASD selectivity calculations are presented. Sometimes the DSLF fits are carried out at more than 1 temperature, and the selectivities are also determined at more than 1 temperature. Important to note that the determination of the QST or isosteric heats of absorption are almost invariably based on virial fits. So in fact, the isotherms are fitted in 2 different ways for 2 different purposes. I'll return to this topic later in my presentation. The next step is to provide breakthrough experimental data to confirm the efficacy of the developed MOF for the specified separation application. Furthermore, grand canonical Monte Carlo simulations and DFT methods are used for getting insights into adsorbate-adsorbent interactions. Let's look at each of these factors in detail for evaluating cadmium MOF for natural gas purification to produce purified methane. The feed mixture consists of methane, ethane, and propane. And in evaluating cadmium MOF, we first need to examine the unary isotherms for each of the guest molecules, and it is common practice to measure the isotherms at least 2 different temperatures. Data for propane, ethane, and methane at 273 Kelvin and 298 Kelvin are plotted here. And the first task is to fit the unary isotherms. The procedure I adopt for fitting the unary isotherms is based on Occam's razor, a principle that states, do not complicate things beyond necessity. Indeed, I choose the simplest model to start with, which is the single site Langmuir model, and only if this model fails to capture the essence of the isotherms at the various temperatures do I proceed to include further complications. So if I need to abandon the single site Langmuir model due to the presence of isotherm inflections, I proceed to examine whether the dual site Langmuir model is of adequate accuracy. Only if this model also fails quantitatively to represent the unary isotherms do I proceed with the two-site Langmuir-Freundlich model. Perhaps I may even try the single-site Langmuir-Freundlich model, but I'm usually reluctant, indeed very reluctant, to include the Freundlich exponents mu A and mu B, because inclusion of such exponents leads to problems when we extrapolate the data to lower pressures. This aspect of particular importance in simulating breakthroughs in fixed bed adsorbers. I must also stress that I do the fitting using an Excel solver and never, underscore never, use a standard fitting procedure where a software spews out the fit parameters. I spend a lot of time in choosing the right parameters that reflect the isotherm model and the physical significance behind the values of the saturation capacities, etc. I will return to this in my subsequent slides. For adsorption of water alcohols within MOFs and zeolites, the isotherms have exhibit steep behavior due to molecular clustering, and it may even be necessary to adopt a three-site Langmuir-Freundlich model. Summarizing, keep matters simple, use Occam's razor, choose the simplest model, increase the level of complexity only if this is strictly required. On close examination of the data on the unary isotherms, I conclude that for methane and ethane, the single site Langmuir is of adequate accuracy, and for propane, the isotherm inflection is present, and I need to use the dual site Langmuir fit for the isotherms. I invariably fit for each gas molecules the isotherm data at all temperatures using a model that includes temperature-dependent Langmuir parameters. For example, for the unary isotherm fits for propane and for methane and ethane, this is the single site Langmuir model, but the Langmuir parameter is temperature dependent, where EA is the energy parameter. So in these two cases, for methane and ethane, the isotherms at both temperatures are described by a set of three parameters: the saturation capacity, QA sat, BA naught, which is this parameter, and the energy parameter EA. This is related to the isosteric heat of absorption. Indeed, for a single site Langmuir model, EA is the isosteric heat of absorption, which for methane turns out to be 27.7 kilojoules per mole, and for ethane it is 33 kilojoules per mole. When plotting the data and fitting using the Excel solver, I always plot the loading against the surface potential that is a proxy for the spreading pressure P. A is the surface area per kilogram of adsorbent, R is the gas constant, T is the temperature. At any given temperature, the surface potential is simply given by this analytic formula. And the goodness of the fit is obvious because the data at two different temperatures collapse into a single curve. This is advantageous when fitting the isotherms, because the unary isotherm data at the lower temperature tends to approach the saturation capacity more closely than the unary isotherm data at the higher temperature. Indeed, for methane, the two sets of data are fitted with a value of the saturation capacity of 4.8 moles per kilogram. For ethane, the saturation capacity in the fit is 3.4. I choose nice whole numbers for the saturation capacity and the energy parameters, and the Excel solver is used to determine the BA naught parameter for which is defined here, this one. For propane, I need to adopt the two-site Langmuir model, and the expression for the surface potential is given here. Watch also my video presentation on the theory behind the spreading pressure concept and the surface potential. The important point to stress is that the unary isotherm data at all temperatures are fitted with temperature dependent parameters by plotting the loading against the surface potential. The isotherm fits using temperature dependent Langmuir parameters can be combined with the Clausius-Clapeyron equation for the isosteric heat of adsorption, and the values of the QST determined by analytic differentiation of the unary isotherm fits. And the values for QST are provided here for methane, ethane, and propane. For propane, we see that there is a clear inflection in the isostatic heat of adsorption. This is a reflection of the inflection in the unary isotherm data. I am not in favor of using virial fits of isotherms to determine the QST. The far better procedure, that is a fundamentally correct one, is to use temperature dependent Langmuir parameters, or indeed Langmuir-Freundlich parameters, to determine the QST. It is common practice in the MOF literature to compare the performance of different MOFs for a given separation task by comparing the values of the adsorption selectivity that are invariably determined using the ideal adsorbed solution theory. The expression for the selectivity is given here. It's the ratio of the molar loadings of components in the adsorbed phase divided by the ratio of the corresponding mole fractions of 1 and 2 in the bulk gas mixture. The important drawback of this of the use of the adsorption selectivity to rank and select MOFs is that for separations in fixed bed adsorbers, the adsorption selectivity is not the only factor that determines the separation performance. Indeed, other factors such as uptake capacities are also important. So how do we choose the appropriate metric for natural gas purification that has 3 components in the feed mixture? In order to understand which metric is appropriate for natural gas purification, I present here transient breakthrough simulations for a mixture of propane, ethane, and methane in the proportion 5, 10, 85 at a temperature of 298 Kelvin. The breakthrough simulation methodology is discussed in detail in my previous publications. Watch also my presentations on transient breakthrough simulations on this YouTube channel. The transient breakthroughs are presented in the form of the dimensionless concentrations at the exit of the adsorber as a function of a modified time parameter that consists of Q0 times T divided by the mass of adsorbent in the bed, where Q0 is the flow rate of the gas mixture at the inlet, say in units of liters per second. T is the time in seconds, and the mass of adsorbent in the bed, M sub ads, is in kilograms, and the x-axis has the units of liters per kilogram. The objective of the separation is to produce purified methane, and say the required purity level is 99.9%, it is clear that the methane of desired purity is recovered till the time that ethane breaks through, so during this time interval. So you might argue that the relevant selectivity is not propane methane selectivity, but rather the selectivity of ethane to methane. So we need to have a MOF that has a high ethane to methane selectivity. The propane methane selectivity is not directly relevant to the production of purified methane. Now, using the shockwave model for a fixed bed adsorber, in this ACS Omega paper in 2020, I developed a metric called the separation potential that quantifies the maximum productivity in a fixed bed adsorber. The application of this concept of separation potential to a three-component mixture of methane, ethane, and propane leads to the following expression for delta Q. The separation potential is that equals the sum of the component loadings of propane and ethane at the given temperature and total pressure for the specified feed mixture composition. These loadings can be determined from the IAST multiplied by a factor which is the ratio of the mole fraction of methane in the feed mixture divided by 1 minus the mole fraction of methane. Now the methane mole fraction is 0.85. So this factor here is 0.85 divided by 0.15. And the separation potential is this product minus the component loading of methane that is also determined from IAST calculations. This separation potential reflects the maximum productivity that is achievable. In actual practice, due to distended breakthroughs, the productivity is reduced below the value dictated by the separation potential calculations. So the message here is that for the separation task, delta Q is the appropriate metric that should be used for evaluating MOFs. And breakthrough experiments for cadmium MOF are shown here for a mixture of propane, ethane, and methane, 5, 10, 85. And the breakthrough experiments are in good agreement with the transient breakthrough simulations presented in the previous slide. During this time interval, it has been established in the breakthrough experiments that 99.9% pure methane can be recovered. The productivity can be determined from the breakthrough experiments, and the value of the productivity is somewhat lower than the delta Q values that are calculated using the IAST, because there are some diffusional limitations that lead to distended breakthroughs in the breakthrough experiments. The breakthrough experimental data are reported in this separation and purification technology paper 2024. As a background, see another paper on natural gas purification that explains why the selectivity of ethane with respect to methane is more relevant in maximizing the methane productivity.